So B3, right, is then the next one that people had voted on. And so this is just a similar setup. The question now is, you have, you know, uh, it's asking you to get the second electron affinity of oxygen, right? So going from O minus to O2 minus, right? So that's O2 minus is the common electron configuration, right, of the ionic form of oxygen, right? So we always think of oxygen, when it becomes an anion, it becomes O2 minus. And so there's two steps to that, right? Because you have to add two electrons. You add one electron, right? That's the first electron affinity. You add the second electron, right? That's the second one. And so just the same way with ionization energy, they're going to be different values, and they may not necessarily even match what you would necessarily think in these cases. And so if you've worked through that problem, you may have been kind of shocked because the spoiler alert, right? The electron affinity is actually going to be positive for that second electron in oxygen, right, to form O2 minus. But we'll talk about that at the end when we work our way through this problem. So we're given all this information right here, right? We're given the O2 bond energy. We're given the delta H of sublimation of magnesium. We're given the ionization energy of both magnesium and then magnesium plus, right? So we're given the first and the second ionization energies. We're given the electron affinity of oxygen atom, right? Neutral oxygen. We're given the lattice energy of magnesium oxide. And then we're given the delta H of formation of magnesium oxide. So basically what this problem is asking you to do is to set up, first off, the reaction and all the different reactions that have to happen to get there for magnesium plus oxygen gas to form magnesium oxide, right? That's the framework we're going to use to get the electron affinity for the second step in those cases. So if we just draw that out, right, what we have is magnesium solid plus O2 gas is going to form magnesium oxide solid, right? And then, so that means, right, we start off with O2 gas. We're only going to have one oxygen in there. And so we're only going to need to use half of the amount of oxygen in this case. So we get that right there. And so then, what we have here is this is simply the delta H of formation of magnesium oxide, right, which we're given in this case. And so now we just work our way through the same way that we were doing for A3. So the first step that we would want to do is do the sublimation of magnesium, because it has to be in the gas phase for all these different steps, right? So we have the sublimation in this case to form magnesium gas plus 1/2 O2 gas, right? And then we go through and then we do the first ionization of magnesium, right? So that forms magnesium plus. And then we go and do the second ionization energy, right? So this is for then magnesium plus. So we get magnesium 2 plus now, plus 1/2 O2 gas. So we're now done with everything that we have to do with magnesium. So the next step, right, we break apart the oxygen into individual oxygen atoms. And so now this is going to then be half of the bond energy of O2. Right, so what we should get is magnesium 2 plus O gas in this case. Right, so now we have that right there. And so now we have to do the electron affinity steps. And so we're going to do the first electron affinity of oxygen, and we're going to form magnesium 2 plus gas plus O minus gas, right? And then we have the second electron affinity, right? So this is now going to be for the O minus ion. So that's magnesium 2 plus gas plus electron affinity, or not electron affinity, oxide, right? O2 minus gas, right? So we have all that. And then the final thing is going to be then the lattice energy of magnesium oxide, right? And so those are the different steps that we're going through, right? So the same thing as before in these cases. So now we set up our equation the same way that we have before. So we go through, and so we have delta H, that looks like an A, delta H of formation of magnesium oxide is going to be equal to the delta H of sublimation of magnesium plus the first ionization energy of magnesium plus the second ionization energy of magnesium plus the 1/2 of the bond energy of O2 plus the electron affinity of oxygen plus the electron affinity of O minus plus the lattice energy of magnesium oxide. Right? So that's that whole equation. What we're aiming for, right, is to figure out what this guy is right here, right? That's the only unknown. And so we rearrange that whole equation, right? So that way we're solving for the electron affinity of O minus in this case. So we rearrange that. What we get is that EaO minus is equal to delta HF of magnesium oxide minus, and then I'm just going to simply in parentheses put everything else from right here, right? So that's the delta H of sublimation of magnesium plus the ionization energy of magnesium plus the ionization energy of magnesium plus 1/2 bond energy of O2 plus the first electron affinity of oxygen plus the lattice energy of magnesium oxide. Right? So we have that. And so now we just simply plug in our numbers. And so one thing that I have to do before I do that, right, is that just as before, the ionization energies are given in electron volts. So I have to convert those into kilojoules per mole. So 7.65 times, what is it, 1.60218 times 10 to the negative 19 joules per electron volt, right? And so this is an EV, so EVs cancel. So what we get is 7.65 times 1.60218 10 to the negative 19 comes out to being 1.23 times 10 to the negative 18 joules, right? Now we need to convert that into moles, right? And so each one of those ionization energies is for an individual atom. And so if we want to convert it into moles, right, we just simply multiply by Avogadro's number. So we have 1.23 times 10 to the negative 18 joules per atom times 6.02 times 10 to the 23rd atoms per mole. And so that comes out to 1.23 times 10 to the negative 18 times 6.02 times 10 to the 23rd. 740,460 joules per mole, right? So we divide that by 1,000. And what we get is that the first ionization energy is equal to 740 point, well, we only need 3 sig figs, right? So it's just simply 740 kilojoules per mole, right? We can do the same thing for the second ionization energy, right? So this is 15.04. And so I'm just going to go ahead and just do that on my calculator real quick instead of writing everything out. So we have 15.04 times 1.60218 times 10 to the negative 19 gives us 2.4096 blah, blah, blah times 10 to the negative 18 joules. Multiply that by Avogadro's number. And what we get is, what is that, 1,000,000 joules or so. So divide that by 1,000. And so what we get is 1,450 kilojoules per mole, right? Because that's the second ionization energy. And so now, right, so we have all those numbers. They're all in the same units. And so we can just simply plug and chug our way through. And so, the value is going to be delta H of formation. So that's negative 859 kilojoules per mole minus delta H of sublimation is 37 kilojoules per mole plus the ionization energy is 740 kilojoules per mole plus the second ionization energy is 1,450 kilojoules per mole plus 1/2 of the bond energy of O2. So that's 494 kilojoules per mole, plus the first electron affinity of oxygen. So that's negative 141 kilojoules per mole, plus the lattice energy of magnesium oxide, which is negative 859 kilojoules per mole. Right, so we have all of that, and so then now we just plug and chug our way through, and what we get is negative 859 minus parentheses 37 plus 740 plus 1450 plus 1/2 times 494 plus negative 141 plus negative 859. And so what I got was something that does not match up with what I have right here. So what did I do wrong? Oh, I wrote down the wrong lattice energy. That's why you need to pay attention. Right, so I wrote down as my lattice energy here at the end, right, negative 859 kilojoules per mole, which is what the delta H of formation is, when in reality, the lattice energy is actually negative 3,934 kilojoules per mole. Part of my brain was kind of like, oh, that's a really low lattice energy, but then I was like, I'll just go with it as I was typing it in. So if I go back and I change that, so 3,934. And so what I get now is 743 kilojoules per mole, right? So that matches what we have, what I have in the answer key right there, right? So again, very important thing, make sure, right, when you're working your way through, you're being very careful with what it is that you're plugging in and you're transferring over in your calculations, because it's very easy to actually transfer the wrong thing and then it gets caught up somewhere and the number is off, right? And so because like the value that I had gotten just now when I was, had it messed up, it was like negative 2,000 something kilojoules per mole, and I knew that 100% was not going to be correct. And the reason why is that the second ionization energies and the third ionization energies, not ionization energies, sorry, electron affinities are always going to be positive numbers, right? So typically for most atoms, electron affinity is actually a negative number, right? It's a stabilizing scenario where you actually release energy from the system when you're putting the electron in. There's some scenarios where that's not the case. However, once you've already put one electron in, putting the second electron in is actually not favorable. And that has to do with the fact that, right, you're already at a negative charge. And so putting in more electrons in that case is actually becoming less and less favorable to do. And so usually, you start having more positive values in those cases for the electron affinity as you go, to higher numbers of them that are being added. Now, in your brain, you may be like, wait a second, but I thought about the octet rule. Isn't that supposed to be the stable thing that happens? And, we see O2 minus everywhere. If it's so unfavorable, why is that the case? Well, if we look at what happens, right, that electron has to come from somewhere, right? That second electron in these instances. And so that second electron, right, is coming from the magnesium, and the stabilization of the lattice, because it's just so great, right? So it's negative, it's almost negative 4,000 kilojoules per mole, negates that whole process and actually makes that a favorable interaction that happens, right, for them to actually stabilize in those cases together. And so that's the interplay. So even though on its own forming O2 minus is not a favorable interaction, right, because you're going from the whole electron affinity, if you were to add both of them up, it still ends up being like a positive 600 kilojoules per mole roughly. The process of going through and stabilizing and forming that lattice overall, right, negates that, right? It's the same thing, right? Ionizing magnesium metal to magnesium 2 plus, and even just like subliming it and everything, right? Those are all like negative, or sorry, like thermodynamically unfavorable processes. But because once they're both magnesium 2 plus and O2 minus, and they come together and they form that ionic lattice, that forms an extremely stable interaction. with them, right? And so that, that's lattice energy is the thing that really drives, the formation of Mg2 plus and O2 minus in these cases. So, that's the thing to always think about, is that just, in isolation, things may look like they're not going to necessarily happen on their own, but as a collective, right, when things come together, things actually, work out in the end. And so, metaphor for life. But yeah, right. And so that's that right there, right? So if you got a positive value for the electron affinity, like, don't freak out or anything, right? That's it's supposed to be that way. It's supposed to become, thermodynamically unfavorable to put more electrons into a system that already has a negative charge, right? As makes sense, right? If you were to take, a negative, a bunch of magnets that are together, right, and then you were to put, another magnet towards it, but like of the same pole in those directions, right? They're not going to want to interact with each other, right? They're going to push away. But if you force them together and stuff like that, then things may organize themselves in a way that makes sense. And so that's how you do B3.